Known as the dark opening Gaia BH1, this is an exceptionally surprising double framework in which a sun-like star circles a dark opening with multiple times the mass of the Sun. The issue with this discovery is that the framework does not fit into the known models of star and paired framework development. Neither the normal envelope model nor speculations can completely make sense of how the dark opening could tie the star to itself without annihilating it. This peculiarity indeed challenges old standards of astronomy, and the discovery proposes that there are still numerous unseen peculiarities in the universe. A double framework is generally a system in which two gigantic divine bodies, like stars, planets, or dark openings, are bound together by their shared attractive energy. The newfound framework at first gives off an impression of being a typical twofold framework, but then facts arise that have left researchers at a loss for a clear explanation. Dark openings the size of BH1 are ordinarily associated with their stars in extremely tight orbits. However, the star circling this dark opening is moving in such a wide and profoundly curved circle that the team is essentially unthinkable. No current hypothesis can make sense of the peculiar dance of the two. The Gaia BH1 framework is around 1,500 light-years from Earth. The peculiarity was found by the Gaia mission, which has been measuring the positions, developments, and brightnesses of more than 1 billion stars in the Milky Way since 2013. The point of Gaia is to make a profoundly exact 3D guide of the universe and subsequently gain insights into the structure, beginning, and advancement of the Milky Way. Moreover, the general planning of our universe is a focus. Gaia's pursuit algorithms sift through any uncommon peculiarities from the informational databases. The double framework grabbed their eye. The dark opening is probably a stellar mass black hole with multiple times the mass of the Sun. The companion star is a G-type main sequence star and is similar to our Sun, with a surface temperature of about 5,850 Kelvin. The star has a place with the lower center of the most glowing stars in the universe. Researchers are currently considering the forces that have helped these two objects to tie together. It's striking that there is no mass exchange between the star and the dark opening. The star is not radiating any measurable mass to the dark opening, and the dark opening has only gravitationally bound the star to itself to the degree that it doesn't harm the star. Gaia made this incredible discovery, which is almost mind-blowing given the number of incredible telescopes and observation satellites we are now using to uncover each and every mystery in the universe. In addition to NASA's James Webb Space Telescope, ESA's new Euclid Space Telescope is providing amazingly detailed pictures from the universe. The Gaia mission is also an initiative of the European Space Agency. The Gaia satellite is placed directly in space and scans our universe continuously as part of the mission. Researchers are searching for normalities in the universe, but they are also looking for the surprising. From reappearing structures, scientists can infer laws and subsequently understand the outline of the universe. The strange thing about Gaia BH1 could be the entry to a new dimension of knowledge. Initially, Gaia BH1 was perceived as a typical binary system, two large objects bound by gravity. They share a common gravitational center and perform a celestial dance that, at first, looks like that of many other binary systems. However, when the data was inspected more closely, it became clear that this was no ordinary dance. Later, the companion star was identified, but at first, it was unclear who the dance partner was. When the black hole was found, the researchers' interest was further piqued. Binary systems of stars and black holes are fascinating. After all, black holes typically consume matter and, consequently, stars. If they bind to stars without hurting them, as in this case, there is usually a clear relationship of forces. The black hole binds the star just enough to allow it to orbit. However, the star is not always drawn into the black hole's gravitational pull. This typically results in recognizable structures, and our scientific models thought they knew the very conditions under which such a dance was possible. But now, thanks to Gaia BH1, they are discovering that they didn't know it nearly as well as they thought. The star circles the black hole on a curved orbit with a high eccentricity of 0.45 and an orbital period of 185.6 days. This situation is not truly possible. The star should escape from the black hole when it's at the farthest point of its orbit, and the black hole should suck the star in when it approaches again. However, neither of these things happens. The star circles the black hole again and again in a safe orbit. So, what binds the two together, if it isn't any of the known physical forces? At first, analysts thought that one or even a few other objects, such as neutron stars or white dwarfs, could give solidness between the two. Anyway, generally, model estimations have so far yielded no significant results. A third or fourth accomplice would tend to undermine the system. The dance of the two stayed a secret, and analysts looked for answers. The next step was to actually take a look at whether the subsequent dance accomplice probably might be a dark opening later. Anyway, unmistakable motions in the circle of the star clearly demonstrated the presence of a dark opening. These motions, known as wobbles, are like an object's fingerprints. The wobble, or, on the other hand, wave of a neutron star looks very different in relation to that of a dark opening. Again, the questions couldn't be addressed. Gaia BH1 attracted the attention of researchers for another exciting explanation. The double system was found in an extremely secluded area in space. Since no standard model of double development can make sense of it, researchers hypothesize that there is a peculiarity in this region of the universe. Gaia BH1 goes beyond normal envelope evolution. Researchers love their hypotheses, and when a system like Gaia BH1 comes along, the scientists of this world immediately end up needing an explanation when their loved hypotheses fail. Heated discussions result. Paired systems with close orbits are typically explained by normal envelope evolution. The hypothesis is summarized as CE. This approach is a model that attempts to make sense of how the elements in parallel systems work. With regard to Gaia BH1, this model was used to figure out how the dark opening and the solar-like star could form their current system. Anyway, there were a few issues. The CE generally makes sense of how a massive star, as the ancestor of the dark opening, turns into a red giant and extends incredibly. Then, a buddy star enters the outer layers of the red giant. This normal envelope surrounds the two stars. Through friction and dynamic associations, the system loses energy, and the orbit of the two objects limits at the same time. The envelope is launched out. The last state is that the envelope is totally shot out. What remains is a close double system. More often than not, the star is a G-type star like in Gaia BH1, and the subsequent object is a heavenly dark opening, or sometimes a weak neutron star. This model doesn't completely apply to Gaia BH1 because the orbit of the solar-like star is excessively wide to have been made by contact in a normal envelope. The buddy star has just about the mass of the Sun, which makes it impossible that it had sufficient energy to totally strip the huge envelope of the forebear star that later turned into a dark opening. In the case of Gaia BH1, there is also no evidence that mass has been moved from the companion star to the dark opening, which is frequently the case in a close orbit. The scientific approach fails completely here, and researchers are at a loss. No solution. Either the triple star hypothesis? We should investigate the next system that has reached its limits with Gaia BH1. The triple star hypothesis is a model that assumes that Gaia BH1 initially rose out of a triple star system that became dynamically unstable and deteriorated, leaving behind the current system. The system thus began with 3 stars, 2 massive stars in a close orbit around the inner pair, and a lighter third star, probably the G-type star, circling the two in a wider orbit. The 2 massive stars in the inner system might have evolved faster than the external star. They exploded as supernovae, abandoning either a dark opening double or a solitary dark opening formed by a merger. The arrangement of the reduced objects inside made the orbit of the external star unstable, resulting in the present-day setup, a solitary dark opening with the solar-like star in a wide orbit. The triple star theory could explain why the companion star is so distant. The G-type star didn't need to enter a normal envelope, thus avoiding the regulations of the normal envelope evolution model. However, by and large, such triple systems are pure theory since the original events can't be recreated with certainty. They thus remain purely hypothetical. So far, known triple star systems with massive stars and highly curved orbits are generally unstable, which does not apply to Gaia BH1. Questions, moreover, remain unanswered with the triple star theory, which is why it's not an adequate explanation. Challenging to investigate dark openings in paired systems. The fact that our science makes systems, it's obvious that we still actually have barely any familiarity with dark openings in parallel systems. Dark openings play a significant role in space science, as they can tell us a lot about the evolution of massive stars, the elements of paired star systems, and even the origin of gravitational waves. Anyway, they are not always easy to identify and are hard to study. Depending on the properties of the system and the motion of the dark opening, specialists use electromagnetic radiation as a source of information. Dynamic dark openings that attract matter from their companion stars produce strong radiation, especially in the X-ray range. This radiation is produced when matter spirals into a gradual addition circle around the dark opening and is heated by extreme gravity. Such dynamic double systems with dark openings are called X-ray binaries. Lethargic dark openings, like the one in the Gaia BH1 system, are purported lethargic or quiet dark openings. They show no dynamic gradual addition and can only be identified by their gravitational impact on the companion star. Exact astrometric data, for example, that from the Person discharge, can investigate the orbits and motion of the apparent star. Anyway, the possibilities quickly reach their limits with regard to dark openings. If the mass of the invisible companion surpasses the critical limit of around 3 solar masses, it's likely to be a dark opening. Scientists also use gravitational waves, or the aforementioned wobbles, to identify dark openings in paired systems. Gravitational waves are produced when two compact objects, such as dark openings, merge. We now have 2 observatories on Earth that are capable of measuring such waves, LIGO in the USA and Virgo in Italy. These observatories measure these waves with the help of the best sensors. Wobbles, on the other hand, are created by the visible motion of a star. The gravitational force of an invisible companion makes the star wobble slightly, causing the average wobbles. The best recordings are on the way.